p85 and talking about molecules. So molecules are formed when nonmetal atoms share valence electrons. And when nonmetal atoms share valence electrons, we call this covalent bonds. And this leads us into how we come up with the names and formulas for these molecules. So the more electropositive element, so this is the element that will have the lower electronegativity, has less ability to pull or attract the electron towards itself, is always placed first in the compound's name and formula, and it functions as the cation. Whereas the more electronegative element, it has the higher electronegativity, so it has a greater ability to attract and pull those negative electrons toward itself, so it's more electronegative. We always place it second in the substance name and formula, and it functions as the anion. The more electronegative element, because it functions as the anion, we adjust its name to end in IDE. Now, molecule naming and the way that we write the formulas is different than our ionic compounds. So first off, we're going to use the Greek prefixes. Okay, so Greek prefixes, I'm just going to do the first letters down. You are probably familiar with most of these. So you have M for mono, D for di, T for tri, T for tetra, P for penta. You have H for hexa, H for hepta, O for octa, N for nona, and D for deca. And they go in order of mono through penta, 1 through 5, hexa to deca, 6 to 10. Okay, so these Greek prefixes are used in the molecular name to indicate the number of atoms of a particular element present in the molecular compound. The first partner only uses a prefix in the name if its subscript in the formula is 2 or higher. The second partner always uses a prefix. And I'm going to say that you are already familiar with this. Okay, so here is a chemical formula, CO2. And without thinking, most of you are right away are going to say the name of CO2. It is carbon dioxide. So carbon is first, its subscript is 1, no prefix. So the first partner only uses a prefix if its subscript is 2 or higher. Here's another example where you have this chemical formula, capital C, capital O, CO, and right away many of you will be able to name this substance. So this is no longer carbon dioxide, but this is carbon monoxide. So the second partner, so even though oxygen's subscript is 1 in carbon monoxide, it still uses a prefix. So the second partner will always use a prefix. So if you can think about how to go between CO2 and carbon dioxide and CO and carbon monoxide, you have a really good handle on this already. Just like when we change the ending to IDE, sometimes we have to adjust one of the prefixes so that we prevent a conflict with the prefix's ending vowel and an element that starts with a vowel. So sometimes we will shorten it, like drop the prefix's final vowel. And then there are some molecular compounds that are only referred to by their common name instead of a molecular name. So here we go. So the sequence is the prefix only if the subscript is 2, and for us, if the subscript is 2 to 10, we use a prefix for the first element. And this first element, it has the lower electronegativity. The second element has a prefix for any subscript 1 through 10, and it has the higher electronegativity, and it's IDE ending. So we're going to just keep going with the same sequence. Match symbols to the correct element names. Don't guess. Use table S. Match the first partner's subscript to the correct prefix name. If the partner's subscript is 1, then it doesn't need a prefix, so no prefix. Match the second partner's subscript value to the correct prefix. Change the second partner's ending to IDE. Okay, so let's start with a couple of examples. So the first two, H2O, we only ever use its common name. So this will simply be water. Another substance we only ever use its common name is NH3 and is known as ammonia. So you've probably heard the name ammonia, and you don't need to have this memorized because you will be able to find this name and this chemical formula on table L. So now let's start with substances in which we will have to come up with the molecular name. So N stands for nitrogen, if I can spell it. O stands for oxygen. So I simply match symbol to the correct name. N subscript is 1, so no prefix, but nitrogen being the second partner requires it. There's only 1 here, so this would be a prefix of mono. And oxygen being the second partner, we need to change this to ide. So final best answer, I didn't do a very good job here with my spacing, but a final answer for this would be nitrogen, and then I'm going to drop that O from the mono and make it monoxide. So nitrogen monoxide. So take a look at the next example. We still have N and O, so we still know it's some sort of nitrogen and oxygen compound. So here I have nitrogen, and then O being the second partner is going to be oxide. Now for prefixes. So now it has a prefix of at least 2, so it's not just nitrogen, it's dinitrogen, and 7 is hepta. So we have dinitrogen heptaoxide. And one more example where I see it's still just nitrogen and oxygen. So we have nitrogen and oxygen as a second partner is oxide. And now I need to deal with prefixes. So nitrogen has a subscript of 2, so once again it would be dinitrogen, but this time oxygen has a subscript of 3, which is the prefix tri, so I would put tri in front of the oxide, so this would be dinitrogen trioxide. Taking a look at page 86, going in the reverse, where you're given a molecular name and you have to come up with the formula. So match the elements' names to the correct symbols. So don't guess, use your table S. match the first partner's prefix to the correct value. And this is what we use as its subscript. If there's no prefix, then we understand that the subscript value is 1. Next, match the second partner's prefix to the correct value, and it is its subscript. Now, the big thing with molecular compounds is these are not empirical. So write yourself a note. These do not, these don't need to be empirical. So all we're doing is translating the name with the correct subscripts and leaving it even if they're able to be reduced. So here we go. So my first element is sulfur, and the second one is oxide. So I know sulfur uses an S, and oxide refers to O. Sulfur, no prefix, so I understand the subscript is 1, and I see a tri in front of the oxygen, and that means 3. So my final answer would be SO3. Next substance, I see the name silicon, and based on table S, its symbol is capital S, lowercase I, and then I see the other element present is iodine, capital I. Silicon, no prefix, so I understand its subscript is 1, and in front of the iodine I see tetra, which means 4. So my final formula would be S, lowercase I, capital I, subscript 4. My next substance is diphosphorus pentoxide, so I see the name phosphorus, and according to table S, it uses a P. I see oxide, which refers to oxygen, which is an O. In front of the phosphorus this time, I see a di, which means 2, so phosphorus's subscript is 2. And in front of the oxygen, I see pent, which means 5. So my final formula is P2O5. This up. My next example, I see the element named chlorine, which is Cl. And then down a little bit farther, I see the name fluoride, which uses the symbol F. Chlorine has no prefix out in front of it, so I understand its subscript is 1. But in front of the fluoride, I see mono, which means 1. So my final formula is ClF. Last example here, we have dinitrogen tetraoxide. So I see nitrogen uses the symbol N. I see oxide, which refers to the element oxygen, which uses an O. In front of the nitrogen, I see the prefix di, which means 2, so nitrogen uses a subscript of 2. In front of oxygen, I see tetra, which means 4, so that is its subscript. And so the final answer is N2O4. Moleculars do not have to be empirical in nature.